Did you know there's a restaurant located 16 feet below sea level? And did you know there's also an underwater railroad tunnel spanning 3.6 miles? You might be curious about how engineers construct structures underwater. Today, we're going on an amazing journey together. Human inventions are truly beautiful, and this is one of them. Let's explore how engineers build underwater structures. If you stay with us until the end, I am ready to reveal the story behind the underwater railroad tunnel I mentioned earlier. The first thing we need to understand is that we can't build anything in the water. Therefore, the main concern for engineers during construction was to avoid or divert the water. Engineers had to find creative ways to work around the water to build and complete the structures. During this time, human ingenuity led to some amazing inventions. Let us explain how they did it. As we mentioned before, we need to create an environment without water. This is where cofferdams come in. Cofferdams are temporary enclosures that allow water to be pumped out, creating a dry environment for construction. As the name suggests, cofferdams work similarly to dams, preventing the flow of water from a particular area. A fully constructed cofferdam looks like a large, walled pit with water surrounding it. So how do engineers build cofferdams? The first step is to erect the guide piles with the help of a pile-driving hammer machine. These guide piles serve as a guide for creating the cofferdam. Once this process is completed, the driven piles come into play. Piles, which look like long vertical columns, are driven into the ground using the same machine used to erect the guide piles, creating a stable foundation for underwater structures. The piles are usually driven into the ocean bed until they reach the bedrock. The order of piling is from the corners to the center. Piles are most often made of steel, and they have a partially hollow interior. When the piles are in place, water leakage is minimized. The next step is removing the water. You might think this is an easy task, but that's not entirely correct. Engineers need to conduct a detailed geotechnical study of the soil within the cofferdam. They must confirm that the area is suitable for supporting the permanent structure that will be built. To measure soil strength, several tests can be conducted, with the cone penetration test being one of the most accurate. This test was initially developed in the 1950s at the Dutch Laboratory for Soil Mechanics in Delft to investigate soft soils. The test method involves pushing an instrumented cone with the tip facing down into the ground at a controlled rate. With this test, engineers can not only discover details about the soil but also determine how deep the piles must be driven. If this step is completely approved, then we can move on to remove the water from the cofferdam. Using pumping machines, the water begins to be removed. However, as the water level lowers, we can observe water leakage between the piles. Can you guess why that is? We'll give you 5 seconds. 1, 2, 3, 4, 5. The leakage is due to the differential pressure of the water. If you guessed correctly, great job. In this scenario, a single layer of driven piles isn't sufficient, so we need to double them. There will be a space between the driven piles that needs to be filled with granular material such as sand, gravel, or broken rock. This will help to stop the water leakage, allowing us to remove the water completely from the cofferdam. But before we proceed, we need to consider the pressure. You might remember learning about pressure in school. The cofferdam faces significant pressure forces from both inside and outside. When the forces are equal, they cancel each other out. However, if we remove all the water from the inside, the internal pressure becomes zero, and the external water pressure can cause the cofferdam to collapse. How do we prevent this? The solution is the bracing frame system, which acts as the hero protecting the cofferdam. With the bracing frame system in place, the cofferdam is now completely strong. Engineers can remove all the water. However, there is a new scenario here. Due to the water pressure differential, water seepage still occurs, and avoiding this seepage is difficult. To manage it, engineers continuously pump out the seepage water. Once the soil above the hard strata is removed, concreting begins. When concreting is done on the hard strata, our underwater project is halfway done. Hooray! Do you know what this special concreting method is called? It's the concrete seal course technique. It's a specialized method used in underwater construction projects to create a robust and waterproof seal. This technique is crucial for ensuring the durability and effectiveness of structures submerged in water. By combining advanced engineering principles with meticulous execution, the concrete seal course technique guarantees the longevity and high performance of these underwater constructions. Now, engineers can carry on with the remaining construction work. Water seepage is now completely and efficiently blocked. Workers lay out the skeleton of high-quality reinforced bars to construct the footing shaft of the bridge pier. Because this pier structure will remain in the water, engineers ensure that the materials used in the construction are of the best quality. These materials need to successfully bear the water pressure as well as the load of the construction. So, what happens once the structure is completely built within the cofferdam? At this point, the cofferdam is no longer needed. But how do engineers remove it without harming the structure? The cofferdam is below the concrete seal course, so its removal must be handled carefully. So instead of removing the cofferdam entirely, engineers cut the driven piles at the appropriate heights. Once all the driven piles are cut off, the cofferdam is removed from the visible area. This is how the cofferdam is effectively removed. This marks the end of one of the main and most famous methods of underwater construction. However, several other major techniques have evolved over the years, enabling construction companies and workers to build in bodies of water both large and small. Two other notable underwater construction methods are caissons and off-site building, float and lower. Caissons are watertight structures that can be lowered into the water while preserving a dry environment inside. Within the dry interior of an open caisson, workers can dig down to reach a solid surface that the caisson will rest upon. Eventually, caissons become part of the foundation of a structure, often a bridge or a dam. Off-site building, float and lower involves constructing and assembling structures off-site, and then transporting them to the construction site. We would love to explain these techniques to you as well. As promised, I am ready to reveal information about the underwater railroad tunnel. The Transbay Tube is an underwater railroad tunnel connecting downtown San Francisco to West Oakland, carrying nearly 30,000 passengers an hour during the morning and evening commutes. Originally built in 1974, the tube is an astounding feat of undersea construction, particularly given concerns about earthquakes in California's Bay Area. The Transbay Tube is an underwater rail tunnel constructed using the immersed tube technique. Built on land in 57 sections, it was transported to the site, submerged, and fastened to the bottom by packing its sides with sand and gravel. Would you like to learn more about the immersed tube technique? Let us know your thoughts in the comments. If you enjoyed this exploration, please like the video and consider subscribing for more content on fascinating science and groundbreaking technologies. Stay tuned for our next adventure and stay safe.